Hi, I'm Jeff Bates. I'm a professor at the University of Utah in materials science and engineering. I am from rural Utah, from a little tiny town called Wellington, on the way from Salt Lake to Moab. I actually didn't grow up skiing. I've never been skiing, but I did get involved in winter sports research in 2016 when a company, so I have a PhD in materials science and engineering, and a company asked me to do some consulting work, which was all about skiing, and the company was DPS, and so I'll talk about that project a little bit. But I wanted to give a quick introduction to skiing and snowboarding. First of all, giving a historical perspective, we can see that skiing has been around for a long time. We have early skis in the pre-20th century, but of course we go clear back to 8000 BC. You can see how the sizes of skis have changed over the years. The materials that have been used for skis over the years have changed significantly. For thousands of years, I would say, they were made out of wood. The construction was simple, single-piece designs. They were meant for transportation and hunting. Waxes were used. They were beeswax. They were used for waterproofing and preventing snow from sticking. They were not there for glide enhancement. I'll talk more about the different ski waxes later. But here's one of the early designs. I don't even want to try to pronounce the name, but it was a Swedish engineer who made these early skis. The next ones we have in the mid-20th century are metal skis. They used aluminum alloys. The advantage was increased torsional stiffness, improved edge hold, as though they were heavier and they were prone to vibration. And as you can guess, with metal, when metal gets wet, and not wet, but when it gets cold, the ice actually sticks to it quite a bit. So we move into the development of composite materials. Fiberglass was used with ABS sidewalls. So fiberglass was used for, it's lighter than metal, and it has a tunable flex. So tunable flex means, so you know what flex is, so it's going to flex. Tunable means you can change the degree of flex that you get in the material. The ABS is a plastic, so it's able to absorb some of the vibration that you get with skiing. I apologize for the low-res image, but you can see that we still have wood. We've got ash wood in there, we've got aspen wood, we've got different woods inside of there. We've got carbon fiber, we have top sheets, sidewalls, bottom sheets, we have all sorts of stuff. So really, there are all these layers. We've got reinforcement layers, so they enhance the strength, the torsional stiffness, and the edge hold. They can use fiberglass, carbon fiber, metal laminates, aramid fibers like Kevlar, basalt fibers. We've got base materials, so they provide the contact surface with the snow, impacting glide and durability. These are made out of ultra high molecular weight polyethylene. You can have extruded or sintered bases. There's a top sheet. The material is usually an ABS or TPU, which is a thermoplastic polyurethane. Thermoplastic polyurethane or epoxy resin. These are meant to protect the core from impact and UV damage. This is also the layer that incorporates the graphics. We have steel edges, where the role is to enable carving and edge hold on hard snow. Materials are hardened steel alloys. They're embedded into the core and bonded with adhesives. Then we have specialized skis. So these are going to be for the different types of skiing that are out there. Alpine, freestyle, cross-country, backcountry, ski jumping, adaptive. So if you look at this one right here, we've got downhill skis. So these are the longest skis. They're designed for maximum speed and stability. Key features are we've got long length, we've got stiffness. They're very stiff for edge hold at high speeds. They have minimal side cut for stability. Material focus is stiff cores, metal laminates, titanium or aluminum for damping, and torsional rigidity. And we have slalom skis, as you can see right here. They're the shortest, most nimble skis designed for quick turns for men, so 5.41 feet and 5.8 feet for women. They are stiff but more forgiving with their flex pattern. They have a deep side cut for rapid turn initiation, and their cores, whether wood or foam, are made of, the responsive cores are made of wood or foam, fiberglass, and there's an emphasis on quick energy transfer. Giant slalom, it's a compromise between downhill and slalom skis for speed and carving turns. So they're an intermediate length between downhill and slalom. The stiffness, they're stiffer than slalom, less stiff than downhill. They've got a moderate side cut. The material focus is a combination of core materials and laminates and for stability and responsiveness. There we have freestyle skiing. They're park and pipe skis. They're designed for jumps, rails, and other park features. They've got a twin tip, symmetrical tips for tails, and tails for skiing switch, first forward or backwards. They have soft medium flex for easy buttering and presses. Reinforced edges to withstand impacts. And the focus is on material focuses on durable cores, reinforced sidewalls, impact-resistant side-based materials. Sorry about that. Mogul skis, we've seen this before at the Olympics. They're designed for navigating bumpy mogul fields. They're shorter than alpine skis. They are more flexible for absorbing bumps. The material focuses lightweight cores, damping materials like Kevlar and rubber to reduce vibration. We have aerial skis. These are longer than freestyle skis for lift and stability during aerial maneuvers. They're specifically shaped for takeoff and landing steep pitches. The material focus is, of course, lightweight, stiff, and able to withstand lots of weight. We have cross-country skis. They're narrow, lightweight skis for skate-style skiing on groomed tracks. They're skis. They have stiff flex for efficient skating. The bases are smooth and waxable for glide. Material focuses on lightweight cores, foam, or honeycomb. They use carbon fiber reinforcement for stiffness and weight reduction. For skis, so these are specialized ski equipment for skiers with disabilities. Mono skis are a single ski with a seat for seated skiing. Bi-skis are two skis with a frame and seat. Outriggers are handheld poles with small skis at the bottom for balance. The material focus for these is strong, durable materials, adjustable components for personalized fit and performance. Here we have factors that all skis have in common. They have high abrasive resistance. They're able to hold their shape and function after rubbing against snow at high speeds and extreme temperatures. Hydrophobic behavior, they repel liquid water, and prevent liquid from accumulating on the surface. Looking at ski waxes, they are specialized materials that are applied to the ski, to the base of the skis. Their primary purpose is to improve gliding performance by reducing friction between the snow and ski. Think of the ski wax as a performance enhancer for your skis. It's like giving your skis a superpower to glide more efficiently over snow. So here we have an example of how ski waxes are prepped. You scrape the base. You scrape all the wax off the base, and anyway, there's roto brushing and stuff that happens, scraping, roto brushing application that happens with ski waxes. So in the 17th century, skiers used pine tar and rosin for grip and glide. The 19th century saw the introduction of paraffin-based waxes, a significant improvement. By the 20th century, we entered an era of synthetic waxes and specialized additives, including fluorinated compounds, high fluorocarbon waxes. Today we have high-tech fluorocarbon waxes through their use. Though their use is becoming controversial due to environmental concerns, there are major environmental concerns with ski waxes. With fluorinated ski waxes, they've all been banned, including in the Olympics, and that's something that ski wax manufacturers are having to navigate around right now. If we look at the physics of ski glide performance, we have right here, we've got all these different contributing factors. But the heart of ski performance, the concept is friction, where friction equals mu n. This equation represents the relationships between the frictional force, F, the coefficient of friction, mu, and the normal force, n. Skiing, we aim to minimize mu to reduce friction and increase speed. There are variables that affect frictional glide: snow conditions, temperature, crystal structure, ski-based material and structure, wax composition and application, and the skier's weight, and of course their technique. Each of these plays a crucial role in determining the overall performance of the ski. As the skis glide over snow, several processes occur. Dry friction between the ski base and snow crystals, that's the first one. The second one, wet friction from thin water film that forms due to pressure and friction. We'll talk about that in a minute. 3, heat generation, which can affect snow conditions. And 4, snow compaction and deformation. Understanding these processes helps us optimize ski wax formulations. If we look at these right here, these are scanning electron microscope images of a ski base. If we look at, this is the same ski base on a different magnification. 5x, we've got this nice pretty base grind on our ski base. 20x, you can see that it's still got some structure. 100x still has some structure, but now we have a lot of irregularities forming and hairs and stuff on the ski base. At the microscopic level, we can look at a couple of things with the ski-snow interface. Surface tension and wetting behaviors come into play. Capillary action occurs within the snow structure. Surfactants in ski waxes lower the surface tension, enhancing water repellency and dirt resistance. Lubrication in skiing can occur through three mechanisms. There's boundary lubrication, mixed lubrication, hydrodynamic lubrication. The goal of ski wax is to promote the most efficient lubrication given the conditions. If we move on to looking at current research, this is one of the projects that I've worked on, and thank DPS for sending us some footage of their processes at their manufacturing facility. They're located here in Salt Lake City, Utah. What we did is back in 2016, they asked us to develop a permanent ski wax material. And so I've always worked in hydrogels that allow for diffusion of molecules into and out of the hydrogel matrix structure. And so looking at different ski base materials, we saw that there were some structural similarities to the ones that I had been working with before. So the question is, can we get this phantom wax to penetrate into the ski base material so that it can be more of a permanent type of base treatment and also not provide or shed those fluorocarbons that you see in ski waxes. Work involves analyzing the impact of different wax compositions on various snow conditions, exploring eco-friendly alternatives to traditional fluorocarbon waxes, and investigating the relationship between ski-based structures and wax performance. This research applies many of the principles we've discussed, aiming to push the boundaries of ski technology while prioritizing sustainability. Introduction, I am happy to talk more about the Phantom project as well. I would encourage you to watch videos on YouTube by DPS. They do a great job of promoting themselves. Now we're going to talk about ski waxes, fluorinated compounds, and PFAS materials. We just talked about some of the changes in skis that have happened over the centuries, in fact, thousands of years, and ski waxes. But if you remember, the original goal of ski wax was because skis were made out of wood, and they transitioned to metal. With wood is an absorbent material. We didn't want to be absorbing any of the liquid from the snow or any meltwater that had formed on the snow surface into the ski materials. We used hydrophobic materials. And when we're looking at metal, alloy skis, when the metal gets cold, the snow tends to stick to it. Ski wax was used to repel the water and to provide just a protective film between the metal ski base material and the snow interface so that they wouldn't stick to each other. Skis have pivoted to being more of a composite material, and they have different structures within them, and the ski bases transition to being made of UHMWPE, which is ultra high molecular weight polyethylene. We still kept the ski wax with 55 to 75, 3 to 4, 6 to 5. So ski wax is 100%. So you think about ski technicians and waxers, like if these things are, these fluorinated compounds are bad to be volatilized, a ski technician and waxers, they're putting them on, they're volatilizing right in their faces. So we're going to have some higher concentrations of PFAS materials in their blood, for example. The environmental impact, 2019, 2020, 2020, 10, 21, 2020, 2023, 2023. The transition efforts, so there have been developments of fluorine-free waxes that are hydrocarbon and bio-based alternatives, education and outreach to athletes, technicians, and the public, and ongoing research into environmental health and health-safe performance solutions. The key takeaways from this discussion is PFAS in ski waxes revolutionized competitive skiing but brought significant environmental and health risks. Regulatory bans are driving innovation in safer, sustainable alternatives, and stakeholder collaboration is crucial for effective transition. All right, now I'm going to talk about what I think is the most exciting part, which is our research. So we've been researching this, like I said, for the last 9 years, And we've been working with different competitive ski teams. We've been working with individuals. We've been working with wax manufacturers and ski manufacturers. And so we've developed a set of tools to be able to test the glide performance of skis. So I'm going to talk about our research objectives. So first, our project set out to answer three specific scientific questions. So what are the material properties of fluorinated waxes, including the coefficient of friction, hydrophobicity, hardness, and surface roughness, at different temperatures and in controlled laboratory conditions? So number two, what material properties lead to enhanced glide performance of fluorinated waxes in real-world field conditions? And three, how do non-fluorinated waxes and base treatments perform in both lab and field settings, and what are the implications for environmental sustainability? So we tested 92 different ski waxes, different products, and to just compare them across the board, fluorinated, non-fluorinated, so we could just get a feel for everything, how everything performed in comparison to each other. So additional goals included compiling a comprehensive database of wax properties and performance, providing evidence-based recommendations to different stakeholders, and supporting compliance with new regulations banning PFAS in ski waxes. So the problem we're trying to solve, fluorinated ski waxes have long been the gold standard for glide performance, especially in wet or variable snow. However, PFAS are persistent environmental pollutants linked to health risks and ecological harm. Recent bans by the EU, FIS, IOC, and EPA have created an urgent need for high-performance, non-fluorinated alternatives. So the challenges that we have with this are identifying which material properties, like I said before, friction, hydrophobicity, hardness, surface roughness, are most critical for glide performance, because this is something that's not well understood in the ski industry. Determining whether non-fluorinated and bio-based waxes can match or exceed the performance of fluorinated waxes under various snow and temperature conditions, and understanding the environmental and health impacts of different wax formulations, especially regarding PFAS contamination. So ultimately, that's what I'm saying, is that's a key challenge. We are not doing the biological health impacts of these things, but we wanted to be mindful of that as we were evaluating these different things. So the scientific questions that we addressed in this project are: how did the friction, hydrophobicity, hardness, and surface roughness of fluorinated waxes compare to non-fluorinated and bio-based waxes? Which material properties most strongly influence glide performance in both lab and field settings? How does temperature affect the key properties, hardness, hydrophobicity, friction, of each wax type? What is the relationship between wax composition, like the chemical structure, and the performance metrics? How do different waxes perform across a range of snow types and locations? What is the environmental persistence of fluorinated versus non-fluorinated waxes as determined by elemental analysis? And are there viable non-fluorinated alternatives that can meet the demands of competitive skiing? So we created some methods that we'll have some videos that we'll show you as well, to show some of our methods. So we did our lab testing. We used a pin-on-disc tribometer, which we've got a video that will show you that. We have 3 pins we put in contact with a disc that we've punched out of a treated ski base that has different waxes on them. So we measure the coefficient of friction as it spins across that at I think a rate of 5 meters per second. We do contact angle goniometer measurements to look and see what's the contact angle, what's the hydrophobicity. We use hardness testers, so Shore A hardness testers, and then we use SEM imaging to quantify the material properties. We've done some field testing where we've conducted on snow trials with both skis and skiers, measuring real-world glide under a variety of snow and temperature conditions. We use something called elemental analysis, where we use FTIR, which is Fourier transform infrared spectroscopy, and EDS, which is energy dispersive spectroscopy, to detect fluorinated hydrocarbons and other residues in ski bases. So we also partnered with the University of Innsbruck, and we sent a bunch of skis over to them to test a linear tribometer. So if you look at our pin-on-disc tribometer, you have 3 pins going over the same surface over and over and over. We have a layer of water in between at that interface. So that, of course, melts and kind of deforms some of the ice that happens with that. And like I said, we're not cooling it down. We're running the same pins over. But if you think about downhill skiing, you go down really quickly and then it cools down. The next person goes down. So it cools very quickly in real life. And so we wanted to use a linear tribometer where we would shoot the skis that had been treated with the waxes that we were exploring in those cases down a 50-meter track, and we have a video that shows what that looks like. But ultimately, I wanted to tell you that what our key findings were. So the hardness, there's a temperature dependence. All waxes become harder as temperatures dropped. Bio-based waxes were often the hardest, but also more brittle at low temperatures. Fluorinated versus non-fluorinated regarding the hardness, so there was no consistent pattern of higher hardness in fluorinated waxes. Chemical structure and chain length were the most important components of that. So the fluorinated doesn't change the hardness. Hydrophobicity, fluorinated waxes were consistently, they had higher water contact angles, confirming superior water repellency and hydrophobicity. Non-fluorinated waxes are improving, but still lag behind in hydrophobicity. Some advanced synthetic formulations are closing the gap, though. The coefficient of friction, so we have fluorinated waxes had overall lower friction at higher speeds, especially in wet snow. Non-fluorinated waxes are comparable or better performance in cold, dry conditions. The performance is highly context dependent. So what I'm just trying to say right there is that we did observe some lower friction in fluorinated ski waxes, and we did observe higher friction in non-fluorinated waxes. But the non-fluorinated waxes tended to be a little bit more condition dependent than the fluorinated. The most important thing that we did find is that when you look at the coefficient of friction versus sliding velocity, we see this little peak that happens right like at low velocities. So this would be like right as you're starting to go down the hill if you're doing downhill skiing. And so there's just this little spike that happens, so like a really quick increase in the coefficient of friction, and then as you go faster, then it starts to decrease, and then it starts to increase once you get really fast. But ultimately, what we did find that we don't know how to explain yet is that the fluorinated waxes didn't have that same little high friction peak that happened we call it the sticky friction at the beginning, so stiction. So fluorinated waxes didn't have the same stiction that the fluorinated waxes had. So that's probably the most significant finding of all of that. So we don't know why or what causes that. So that's something that's subject to further investigation. So looking at the surface roughness, all waxes reduce the roughness of unwaxed bases. Non-fluorinated solids often produce the smoothest finishes. Abrasion resistance, there's no direct link to fluorination. The durability depended on chemical structure and physical formulation, not just the presence.
Hi, my name is Johnny Stanzione, and I'm an undergraduate researcher here in Professor Jeff Bates' lab. The majority of our in-lab testing is performed using a pin-on-disc tribometer. The lab pin-on-disc tribometer, right here next to me, allows us to measure the frictional force exerted by a disc of ski base relative to the sliding rotational velocity of the measuring system, which in this case is a pin. This measuring system consists of two parts: a stationary base plate to which the disc of ski base material is attached, as well as a rotating measuring system unit that involves the disc and the pins. To test a ski base sample, we first load a disc of ultra-high molecular weight polyethylene ski base material into the base plate, which you can see here. We then add about 200 microliters of water to help simulate the snow surface. As you can see here, the upper unit is the rotational unit on the instrument. You can see the plastic pins, there are 3 of them, attached to this rotating disc. During the test, that disc will rotate to help represent the sliding of a ski base over snow. Once the instrument is set up and the sample is fully prepared, we begin the test by pressing the start button. You can then name it and then let the instrument initialize by pressing continue. The upper unit will then move down to make contact with the base plate. During this part of the initialization, the instrument is ensuring it achieves the correct normal force on the base plate. Now, the actual test has begun. During the test, the rotating measurement system ramps logarithmically from a velocity of 10 to the negative fifth meters per second all the way up to 5 meters per second, collecting 81 data points along the way. This diagram represents the friction factor measured by the device relative to the sliding velocity in meters per second. Friction factor, a dimensionless number, is represented by the Greek letter mu. It is defined as the ratio of frictional force measured by the tribometer to the normal force applied to the ski base. The higher the friction factor, the higher the drag, so therefore the slower the ski. Vice versa for a low friction factor. Low friction factor, lower drag, the faster the ski. The raw data is given to us directly from the instrument in both diagram and table form. In the table, we can see that the instrument provides the sliding velocity, frictional force, normal force, and also calculates the friction factor for us. Typically, we analyze the data after completing multiple tests on different sample sets. As you can see here, the data is similarly graphed on a coefficient of friction versus sliding velocity axes. As you can see here, there are 3 different samples. Sample 1 in blue, sample 2 in red, and a control sample, which is a naked ski base, in green. Because the red samples, sample 2, had the lowest coefficient of friction versus sliding velocity, especially at the higher velocities, more indicative of actual skiing speeds, we can tell that that is the highest performer. Additionally, the red, blue, and green error bars are shown to help us better distinguish the trends in the data.
Okay, welcome class. Because I'm away this week for research, what we're studying today is like nanomaterials is this week, and so closely related to nanomaterials is actually things at a micron level as well, which is a little bit larger than nano. And so we're here in Austria, beautiful mountains, lots of skiing happening, and we're studying at a facility at the University of Innsbruck, and we're studying tribology, which is a study of friction. And so we're specifically studying wax and ski base and how it interacts with snow. We have a lot of really expensive and high-end equipment here that measures down to the micron level, which is 1,000th of a millimeter. And we'll see some pictures and images that I'll show you in a second. So here's this tribometer. It's a one-in-the-world type of equipment for measuring friction on snow. So come on inside and we'll check out some of the snow. So don't mind the noise. We're actually right next to the airport, so ignore the cars on the road. So one of the key variables, one of the problems actually, is that there's so many different variables when we're measuring skis and wax and snow. If you're measuring those things outside on the mountain slope, there's so many different variables like sun and moisture and the grain size of the snow. So we're able to control all of these things inside this facility. Specifically, what we're going to do is look at the snow texture first. So we characterize the snow using a machine that actually we covered in the medical technology, which is a CT scanner, so computerized tomography. So what we're doing is we're looking, so come on over here and I'll show you, we're looking at a CT scan, which is essentially a 3-dimensional X-ray of the snow. So if you can see the computer here, what we've got on the left-hand side we have a 3D scan of the snow itself using a CT scanner. So we've x-rayed the snow to see at 3 dimensions what does it look like. You'll notice it doesn't really look like the fancy snowflakes you have at Christmas. Instead, it looks like round and worn out. It's because it's about 6 weeks old, so it gets the edges rounded. It's also man-made snow, so man-made snow looks very, very different. Any of you that ski, you'd notice that man-made snow on the slopes is very different than fresh, fluffy stuff. And then over here on the right, we've passed over the snow with skis doing our test, and you can notice how they're significantly flatter. So this is one of the tools that we're using to just give us an idea of the characterization of the snow. Another tool that we're using is a 3D microscope. I'll throw some images into the video, but essentially what we've got here is a 3-dimensional microscope that's able to measure, we're zooming in at about 1,000 times, and we're able to see down to a really, really tiny level and determine the 3D structure of the base of the skis. So in a few minutes, we'll take a look inside the facility itself, and we'll look at a special tool that we use to measure the ski base. We measure down to the micron level of the ski surface to see the grooves, to see the wax, the patterns, and then we'll also measure the snow as well using that same machine. So one of the interesting things about doing this research is what affects how fast a ski goes. Not just your skill, but like, does the wax affect it? Does the structure of the base affect it? If you remember from the video from earlier in the week, we know that at a nano scale, for example, structures on the wings of a butterfly, if you remember from that video, they affect how the wind flows over the air flows over the wings of this butterfly. And it doesn't have so much to do with the material that it's made of as much as it does the geometry and the shape of that wing. Not something we see with our eyes, but when you zoom in at a nano scale, something that you can see with electron microscopes. And I'll show you some images of electron microscopes of ski bases also in a few minutes. Okay, that's good.
Action.
Okay, so we're inside the freezer, temperature controlled -5, goes all the way down to -25, all the way up to -1. And so in this about 25 meter long bed, we essentially can come on in and show. We got the ski tested on here. We're applying a specific pressure down to simulate the weight of a skier, about 80 kilograms. And then we're running this machine during our test at anywhere from 5 meters a second, which is like 10 miles an hour, I think, up to 25 meters per second, which is like 55 miles an hour, I think. So essentially this machine will speed up that ski, and then we're measuring the friction, the resistance due to the force of friction, which is a result of the ski being in contact with the snow. So we've got here our handy dandy ski. So we've just finished a test. We can't show you the test in person because safety, but I'll include a little bit of a video showing you that test. So what we're going to do here is measure the surface finish essentially of the ski. So we're looking for what does the pattern on the surface of the ski look like. This particular video is not going to be super interesting because the surface is not likely to be all of that unique, but we've got a couple different ways that we can measure the surface roughness. And like I mentioned earlier, we're measuring actually down to the micron level. So this is a special tool called the gel sight. It's just basically a special device that will imprint the surface of this ski into this pad right here. So I'm gonna bring this pad down here to the base of the ski. And then if you look at the image there on the computer, you can see there, what I'm doing is I'm bringing into focus the base of the ski. So this here is the middle of the ski. There's a bit of a groove in these cross-country skis. And so I'm gonna take a picture of that, and then we'll analyze that for surface finish and the surface texture. We'll also use this device to take a picture of the snow itself. And that might be a little bit more interesting. So I'll analyze that data later on. Now let's come over here to the snow. So we want to look at the snow surface and see what the particles of the snow look like. And so I'm going to press this awesome little device here into the side of the snow and come over here and look at the laptop if you can. So this is what the surface of the snow looks like up close using this device. Pretty awesome technique there. So we'll analyze all this data to figure out just like I said, what is the interaction between the ski, the wax, and the snow, and how does it affect the coefficient of friction? So we're not quite yet at designing ski bases at the nano level at all, even at the micron level at all, but maybe in the future that might be something that scientists and engineers will look at. Cool.
In performance and durability. Number 4, can new non-fluorinated additives, ceramics or silicones, further improve hydrophobicity and friction reduction? Number 5, how can sensors or simple devices be designed to measure ski-based friction or hydrophobicity in the classroom? We're trying to do this actually for field testing. Regarding the topic of sustainability and environmental impact. Number 6, what is the environmental fate of ski wax residues in snow, soil, and water after the ski season? Number 7, how do different waxes affect the microbial communities in snow and soil at ski resorts? Number 8, can natural or biodegradable waxes provide sufficient performance for recreational skiing while minimizing environmental impact? Number 9, what are effective methods for remediating PFAS contamination at ski resorts? Number 10, how does the life cycle carbon footprint of fluorinated versus non-fluorinated waxes compare? Regarding human health, I've got 3 questions. Number 11, what are the health risks of inhaling wax fumes and how can ventilation or PPE reduce exposure in ski workshops? Number 12, how do PFAS from ski waxes enter the human body and what are the potential health consequences? Number 13, can educational interventions change athlete and technician behavior regarding safe wax handling and environmental responsibility? Performance and optimization, I've got 2 questions. Number 14, how can data science and machine learning be used to predict optimal wax selection based on weather and snow data? Number 15, what are the best practices for testing and comparing ski waxes in a school laboratory setting? Our research demonstrates the material science is at the heart of both performance and sustainability in skiing. We would love to be able to jump on board with doing any of this research, whether they're students or teachers or researchers, explore the real world scientific questions and hands-on experimentation. We were hoping that we can inspire the next generation of innovators and environmental stewards. If you have any questions, please feel free to send me an email.